Imagine driving an electric vehicle with 6% of battery left, worried that you might not make it to the nearest charging station. When you were finally able to make it, you plug in the charger only to realize that the charge time is 8 hours long. While governments are doing their best to provide charging stations near every household, it simply isn't accessible to all EV owners in Singapore. Hence, charging at malls or petrol stations remains their best option to recharge their EVs. What if there is a way to remove these issues? What if we could reduce the charging time and improve the consistency of the range of a fully charged battery? The issue with decreased range and long charging time is due to the consumption of energy to maintain the battery at optimal performance and charging temperatures. This results in lesser energy for the car to travel. The battery itself has an optimal temperature it wants to operate at. A research done by Ansai Wang and team suggests that the optimal temperature range is about 25 to 40 degrees. Any higher this would lead to thermal runaway, thereby lowering the thermal efficiency. The overall consumption of energy needs to be reduced not just for the sake of customer satisfaction, but also because this can result in a sustainability issue in the future. In order to solve this, the coolant used in EV battery systems needs to be improved. In collaboration with Brentag and the guidance of Professor Aravind, our team has come up with a coolant for battery packs that performs better than the current coolant used by the leaders of the industry. Currently, industry leaders such as Tesla use a mixture of ethylene glycol and water at a 50-50 ratio, which is good, but not enough to keep up with the energy demand. We did multiple prototypes to test out the different variations of coolants. Our prototype is a flow simulation of a radiator found in electric vehicles. We can see from the thermal image that there is a decrease in temperature as the coolant runs through the radiator. In our second prototype, we used a 50-50 mixture of water and ethylene glycol to test out its performance. In prototype 2, we incorporated the aluminium oxide nanoparticle into water and EG mixture to use it as a coolant. The performance was better as seen from the thermal imaging, with a greater area of blue. This, in turn, reduces the energy needed to produce the battery and, subsequently, the carbon emissions associated with its production. But the benefits don't stop there. With increased efficiency, the batteries don't need to be as large, resulting in lighter vehicles. And lighter vehicles consume less energy, further reducing their carbon footprint. By harnessing the power of nanotechnology, we can create cleaner, more efficient electric vehicles, paving the way for a greener future.